Okay guys, we're going to head off into the final chapter of position. I think I explained to you that the chapter on position is far and away the most complex. It allows us to do a lot of things, but I don't want to go into that level of detail for the purposes of this course because if you ever encounter it, you'd actually have to go back to the standard anyway and try to make sense of it. But what I do want to do is go through this one last example. And this is an example where we're going to use least material condition. And least material condition is almost always used to guarantee that we have a minimum amount of material in some instance where we have two features interacting, where two holes might be getting close to each other, or where we have in this case we have a male feature, a boss, and a drilled hole in it. And all too often, if you have a narrow feature and you're trying to drill a hole in it, especially if the feature is produced on some other machine at some other time, or is cast in or forged in, we have a tolerance of the position of the boss and we have a tolerance of the position of the hole. And if those tolerances work against us, and one goes one way, one goes the other, we could end up with a very thin wall condition, or we could end up with an actual breakout. So if this passage were, say, a pressurized passage for oil or coolant or something like that, it could actually leak at that location. So it's something that engineers do think about and worry about. What I've drawn here on the board, of course, is right out of your handout. It's figure 713, so you can kind of follow along with that. What I'm going to do though is step through the different states that this thing can be in. We can end up with the boss and the hole at certain conditions and they can be perfectly aligned, or in the worst case they can be misaligned by whatever the tolerance will allow. And we're going to prove that by using the least material condition modifier, we can guarantee that we'll have a minimum wall thickness in all instances, no matter what size the feature is, and no matter what size the tolerance zone is at that condition, it will always guarantee us a minimum wall thickness. All right, so just to sort of review what you're looking at here, probably a little easier to read in the book, but we have a thin boss. That boss is a projection off of a surface, and that's the male feature, and that's a 30 millimeter plus 1.5 minus nothing male feature. The female feature is the drilled hole. It's 20 millimeters plus nothing minus half a millimeter on the drawing. And the positional control is at least material condition. We have a 1.5 millimeter diameter tolerance zone at least material condition. In other words, at least material condition, which is 30 millimeters, that is the smallest that boss can be, is 30 millimeters, because the tolerance says you can only go up from there. So the tolerance is stated, or the dimension is stated at least material condition, and at least material condition we have a 1.5 tolerance. Remember, and never forget, certainly before the final, that when you look at this, you read it by saying, I have a 1.5 millimeter tolerance at least material condition. That is the smallest tolerance zone I'm ever going to get. And as I go away from least material condition and go to maximum, head towards maximum material condition, in other words, as this boss gets bigger and bigger, I get an additional amount of positional tolerance on a one-for-one basis. So if I make the boss 1 millimeter bigger, I get an additional 1 millimeter for the tolerance zone of position. And likewise here, only just the opposite. Here we have a 20 millimeter hole plus nothing minus 0.5, so that 20 millimeters is also at least material condition. In other words, that's the biggest that hole can be. And when the hole is at 20 millimeters, we get a 1/4 of a millimeter tolerance zone. That tolerance zone also, if we make the hole smaller, if we drill it at 19.75, we'll get that additional quarter tolerance and we'll add it to this and we'll actually double that tolerance. So that's the way it works. It works just like maximum material condition, only the stated tolerance applies only at least material condition in this case. Now let me take just a quick aside here, just so that this will refresh your memory and reinforce the notion about constraints. You always want to look at where your datums are. In case in these instances we've invoked three datums, A, B, and C. A is the bottom of the part, so here's the block. Bottom of the part is constrained. We also constrained at B, and we're constrained at C. So in other words, if we're constrained, if we have to touch those surfaces, the part is fully constrained. So just as a reminder, to always sort of evaluate what your constraint is. But it's not going to impact anything here because there are no material condition modifiers on the datum, or could there be. All right, so let's look at what happens now when we start drifting around and the features get bigger or smaller. The positional tolerance is going to adjust accordingly. Let's see what can happen here. And again, our goal is to guarantee that we have at least a minimum wall thickness. So let's look at sort of the as drawn condition. And I've done this over here. I've got a 30 millimeter boss, a 20 millimeter hole, and let's say those are perfectly aligned. No, it can't happen, but let's say they are. What would the resulting wall thickness be? Well, it'd be 30 minus 20 divided by 2. That's a 5/1000th wall thickness. So when these two features are perfectly aligned and at their least material condition, in other words, smallest boss, biggest hole, we are going to net out a 5 millimeter wall thickness. Okay, so, but let's say that they are perfectly aligned, but they're still at least material condition. It means now that we have to look at how much tolerance we're allowed when the features are at least material condition. So let's look at the boss first. It is 1.5 millimeters. That means that it's a cylindrical tolerance zone, 1.5 millimeters in size, because the boss is at least material condition. And the center line of that feature now has to stay within that circle. So how far can it move from its perfect position? Well, it can move half of that amount. It can move the radius. So it can move, let's say it moves this direction. So the boss now is over here. And it's moved over that much. So already there's some eccentricity between the hole and the boss. And it can move half that difference of, or half that distance of 1.5 for a total of 0.75 millimeters. Okay, so that's the boss. The boss has a tolerance and it can shift over 3/4 of a millimeter and stay within tolerance. Likewise, the hole has a tolerance. It's a smaller tolerance. So it's a 1/4 millimeter at least material condition, which the hole in this example is. So it can move 1/8 of an inch. So let's say we have a boss that moves this way, and we have a hole that moves this way, and that's going to be sort of our worst case. That's one goes one way, one goes the other. That's the least, or the worst case for wall thickness. So we can lose then, or we will lose 7/8 of a millimeter, 0.875 radially from our tolerance zone. So when they're perfect, it's 5 millimeters. So we'll subtract 0.875 from that 5, and we'll end up with 4 1/8, 4.125. So in the worst case, where the holes are going the wrong way, we're going to end up with a wall thickness, worst case wall thickness at least material condition, of 4 1/8. Okay, and I've written that here, and I've written that here. At least material condition, 4 1/8 wall thickness. At least material condition, we have a 5 millimeters. If everything is perfect, it's only going to get worse once things start moving around. So the worst case will be 4 1/8. Okay, so now let's look at the other condition where we get away from least material condition and we go to maximum material condition. That means that the tolerance zone is going to get bigger on a 1-for-1 basis. And what we want to make sure is that if that tolerance zone gets bigger, that the wall thicknesses are going to get thinner and thinner. So let's look at that case. So we look at over here, we see that the boss at maximum material condition is positive. It can go up another 1.5 millimeters, so its diameter is 31.5, and the hole gets smaller as it goes towards maximum material condition, and the smallest it can get is 19.5. And if you subtract those out, and again when they're perfectly centered, we're going to end up with a 6 millimeter wall thickness. Okay, so that's getting better. We start out with 5 millimeters at least material condition, perfect alignment. We end up with 6 millimeters at maximum material condition, perfect alignment. Okay, so now you can kind of see where we're going here. You can see that at maximum material condition, then we have an additional millimeter of wall thickness. So the holes can actually, the boss and the hole can both drift a little bit more and still end up with the minimum wall thickness that we're looking for, which was 4 1/8. All right, so let's do that math here. We'll see that at diameter 31.5, if we add the change in size to the tolerance, that 1.5 millimeters adds to that. So that's a 3 millimeter diametral tolerance. That means the hole can move the radius, which is 1.5. Likewise, at 19.5 millimeters for the hole size, we get to add that 0.5 millimeter for a 0.75 diameter tolerance zone. Half of that is 3/8, 0.375. We add that up, and that is 2 7/8, so that the wall thickness will vary by that difference between 6 millimeters and 2.875. If we do that arithmetic, 6 minus 2.875 is 4 1/8. So we actually ended up with the same wall thickness, even though the bosses got bigger, they were allowed to move further. And the net result is that no matter what state the material condition is in the boss, by allowing the tolerance zone to adjust based on that material condition, we can guarantee that result of a minimum wall thickness. So again, it's very convoluted. You've got a lot of things going on here. You've got size changing, you've got tolerance zones changing, but if you do the arithmetic, you'll see that this will allow you to shift by the amount equal to the increase in the material, and the net effect is that you have a constant wall thickness, or a constant minimum wall thickness. Okay, so that's about as sophisticated as we want to get in this video and in this class. We've got one more video. I'm going to do a very brief video on runout. Runout is a fairly simple control, but it is a very common technique for verifying what is effectively position. We can also use it to check orientation, and we'll talk about that a little bit. There won't be any material in the test about that, so I want you to just take this for as for completeness. That will complete the different groups of controls, and there are two different ones in runout, just like there is in profile. So try to absorb some of this, make sure that you're following along. But again, you won't be asked to do this on the final or anything like that. I just wanted you to see sort of a real world example of the tolerance zone and the material condition modifiers working together to guarantee a result.